Hello. So, we begin this lecture course on finite element method and computational structural dynamics with the basic concepts of what is meant by scientific computations. Finite element method is of course a approximate method, an approximate method for solution of partial differential equations, and partial differential equations are the soul of all engineering analysis, all domains of science and engineering. So, finite element method is an approximate technique, and when we talk of approximations, it is very crucial to understand what constitutes a good approximation. And in order to understand what is the what are the measures that we use to qualify to understand the quality of approximation, we will start this course with a discussion on basic understanding what is involved in scientific computations, what are the sources of errors, and some basic concepts from linear algebra, which is very important for constructing any approximation. So, to begin with, as I said earlier, we are looking at approximate solution, and everything is approximate. So, all solutions, anything that we do on digital computers, any numerical computation, it is an approximate solution, and it is good enough for all practical purposes. We can design all our complex engineering systems based on these approximate results. So, it is not as bad as it sounds. Approximation, we can have a really good approximation, provided we take care. So, that when we say we take care, when I say when we take care, it actually means that we should be able to control the errors from propagating and find out ways and understand what is going on in our computations, in the process of computations, and take appropriate measures to keep the errors from blowing up. Now, just to put this in context, you would recall, I am sure everybody must have done this sort of activity, punching a very large number on your scientific calculator and then repeatedly taking square root and ending up with 1. And after that, no matter how many times you try to square it, you can never get the original result. So, that is although we may not have paid much attention to the significance of this result, but that is the crux that hits at the crux of the problem, the loss of accuracy in subsequent use of results of previous analysis. So, just to drive home the point, let me take this example. I am retaining only 4 significant digits in the calculations, just to keep the numbers from blowing to keep the numbers within one slide. So, what I am doing here is take a number x, that is in this case I am taking 2 and take its square root and then square it back, take it and then square it back. So, 1.414 is the square root and then its square again is 1.999. So, we have some loss of accuracy here, and then what I do is now take this number and take its square root again and then make it power 4, and so on. I keep on doing it up to 9 cycles, and ideally if everything was all right, if we had no loss of accuracy, if we were working with exact calculations, then the last column should have been ideally been equal to 2.0, absolutely no difference from the original number that we started. Now, the problem is as you can see, in as early as the 9th cycle, we have a number which is obviously we cannot by any stretch of imagination can call it a good approximation of number 2. Up to 5 iterations, it is close enough if we can call it a good approximation of the number 2, but 9th cycle the number is very different, and by no stretch of imagination can it be called a good approximation for number 2, and that is the problem that I have been talking about, the loss of accuracy during numerical computations on digital computers, and then if we use the results of previous computation in subsequent computation, then these errors are propagated and they keep on accumulating, and that is a major source of problem, and we have to guard against this particular source of error, because it is very surreptitious. This error creeps in surreptitiously, we do not know, we may never be aware of, we have not done anything wrong as far as the operators are concerned, mathematical operations are concerned. We are using all the operations consistently and correctly. The also the error is kind of hidden in the computation, hidden in the details, and if we are not careful, if one is not aware of this loss of precision during the computation, we may never be able to figure out why the results are not coming out as expected, why the results are off the mark sometimes, and if we know the result, if we do not know the result, then it is a catastrophe waiting to happen, because unwittingly we might be using a wrong result for designing all our complex systems, complex engineering systems. So, why do these errors occur? As we all know, it is in information age, and digital computers are the basic tool of this information age, and they are the information processing machine. Just as in the industrial age, the machines, they were essentially energy transformation machines, in information age digital computers are the machines which transform information from one form, one set of information is transformed into another set of information, and they are very good and useful at that. But anything man made is obviously finite in size and speed, and computers, digital computers are also finite in size and speed. No matter what computer we are talking about, it can be as small, as trivial as cell phones in our pockets, or tablets, or very expensive supercomputer, largest supercomputer that we have. No matter what, they are all finite machines, finite in size and finite in speed. The implications of this finite that I am harping upon is very important in the context of our concept of number line. Real number line, we have been brought up with the basic idea that number line is infinite, it extends from minus infinity to plus infinity, and then in between any two numbers we can pack in another set of infinite set of numbers. So, now that is a problem with computers which is finite. How do we represent infinity? So, the problem is infinity can only be approximated, infinity cannot be represented on a finite machine. Now, that is a problem, infinity can only be approximated. So, what are the implications? So, just to explain the, to appreciate the implication of this simple statement that we have to approximate the infinity. So, reiterating the earlier question, how many numbers can we pack in between any two numbers, let us say 10.0 and 11.0? Immediate reply would come as infinity. That is what we have been taught. We understand the number system and real numbers, and why just 10 and 11, 10.0 and 10.1, we can still fit in infinite numbers in between that. But is it possible in a digital computer? As I said, infinity is not possible in any form. So, it is not just the range, not just the end values minus infinity to plus infinity, it is the numbers in between any two consecutive numbers that we may choose. So, even in that the infinite population, infinite fill ins that we take for granted in case of real number line is not available in a digital computer. So, this follows from basically the numbers, how the numbers are stored in digital computers, and that is what we need to understand in order to appreciate why the errors occur, why the errors in computation occur because of in digital computations or computations on digital computers. And once we understand that, then we may be able to figure out, or we may be able to rearrange our computations in such a way that these errors are kept in check, and we can prevent errors from blowing up. So, more on that later. So, another thing that curious thing about digital computers is the number representation as integers and real numbers. So, is 10 by 11 same as 10.0 by 11.0? These are two different types of number representation. One is, first one is the integer representation, 10 as an integer and 11 as an integer, and their ratio as an integer division. And the second one is 10.0, that is a real number with the whole part and fractional part, and 11.0, that is a real number with whole part and fractional part, and their division as a division of real number ratio. So, floating point operation as we call it. So, these two behave differently. Integer arithmetic works differently than the floating point arithmetic on a digital computer, again based on the way the numbers are represented. And another problem, another typical issue is, we understand, the human beings understand the decimal number system, base 10 number system. That is how we started counting, because we have 10 fingers, and we earliest human beings started counting on fingers, and that is how we have grown to understand counting in the multiples of 10. So, base digital base decimal number system is very hardwired, kind of hardwired into our brains, and we understand numbers very easily when they are expressed in decimal number system. Computers on the other hand, they are they operate, digital computers, modern day digital computers, they all operate on binary representation. Binary representation because it is very easy, it is possible to design a very robust and reliable circuitry which only has to distinguish between two voltage levels, high and low, high voltage and low voltage, and that is a binary representation. So, now we have a dichotomy in the sense that the input that a human being has to provide to computer has to be in decimal number system, the output has to be in decimal number system, and the internal calculations, internal representation in the computer has to be in a binary representation. So, we have this conversion from decimal to binary and then binary to decimal during the input output, and that is how digital computers work. So, it is only the representation when interfacing with interacting with the human beings, that is the digital numbers, decimal numbers are used. Internal representation is all binary. And just to for the sake of completeness, that is a very simple schematic representation of the organization of a digital computer, which we call as von Neumann stored program architecture. All computers, present day computers, are based on this architecture. So, as you can see, this is this comprises of a basic central processing unit, and there is a control unit and arithmetic logic unit that does the basic operation, and there is a small set of very small set of memory that we call as registers. So, this is very high speed memory. In general, you can as a rule of thumb, we can say that the storage or the input output speed of input output increases, or time for input output increases the further it is the storage is away from the control unit or the central processing unit. So, registers are the fastest memory, fastest storage area, which is actually built into the chip, basic microchip. Then we have level 2 cache, and then RAM, and then the large storage, that is we call secondary storage. So, RAM is of course faster to access than the storage, large storage, and secondary storage is of course slower to access, but then there are peripheral devices. All of these are connected through what we call as communication bus, that allows communication between different units to with the central processing unit, and all peripheral devices are the slowest of all. They are even slower than the storage, large storage, main storage. So, that is the basic computer architecture that we have, and all modern day computers, they are based on this computer architecture, and as I said, it is all based on binary representation. Everything happens in the binary mode. So, how are the numbers represented? So, first is, as I said, integer representation. So, integers, if you have a little bit some exposure to programming, then you might realize, you might recall that there are different types of integers. We can have signed integers, we can have unsigned integers, and then we can have long integer and short integer, that is depending on different lengths of the bits that are set aside for one size. So, just an example for different types of integers, I used this 3-bit system representation. So, for different bit pattern, you can see the mapping of decimal equivalent decimal numbers. So, on the first, in the first column, it is all binary representation, all bit patterns that we can possibly have for 3 bits if the word length is 3 bits. Second column is the unsigned integer in decimal number system. So, 3 bits, that would be ranging from 0 to 2 raised to the power 3 minus 1. So, that is 0 to 7. So, total of 8 representation, 2 raised to the power 3. So, these are the total possible representation, 0 to 7, and then of course, integer can be, or theoretically an integer extends from both negative range and positive up to positive range. So, we have to technically correct representation of an integer is of course signed integer. Then there are different ways of representing the signed integers, again based on convention. We can look at it as a first I mean the leftmost bit that we have as a sign bit, and then rest of the 2 as the number representation. So, if I consider 0 as the positive sign and 1 as an indication of negative sign, so that would represent the first 3 numbers as 0 plus 0 plus 1 plus 2 and plus 3, and subsequently we would have minus 0, minus 1, minus 2, minus 3. So, very simple representation. It is all again it is based on convention. Once we agree to a common representation, then everybody understands what is the interpretation, how these bit patterns are to be interpreted, and then of course, once these rules are defined, then there is no confusion and it can be done, it can be understood very well. The only problem with sign and modulus form is a little inconvenient notion that we have 2 representations of 0, we have plus 0 and minus 0, otherwise it is all fine. Another representation is 2's complement, again based on some representation of some standard transformation rule, and third one is XSK. XSK is something that is similar to shift of origin. So, instead of having this unsigned decimal representation from 0 to 7, if I say instead of having 0 at 0 representation, I move my origin to somewhere in between, middle of the range, and that is the constant shift that I impart, and that brings the entire representation. So, from minus, so I extend my range almost halfway from minus into some minus integer to some positive integer. So, almost equal value. So, that is how these are the 3 different representations for signed integers, and all of them are used in different context. So, that is the reason we are looking at these, and we will have more on this little bit in a little while. So, all integer arithmetic, the basic operation of integer arithmetic is it can be reduced to a sequence of additions. Subtraction between two integers can be considered as addition of a negative integer to another integer. Multiplication can be represented as repeated additions, and division as a repeated subtraction, and that actually allows us to build a computer with just addition. So, addition of integers is exact on computers. So, integer arithmetic is exact, there is no error whatsoever as far as addition operation is concerned, as long as the result can be accommodated in the word length whatever we have assigned, the bit width. More on this. This is an example of what I mean that by if the result can be accommodated as long as in the assigned bit width. As you can see, this overflow, whenever we have this addition, there is this carryover of fourth bit. Now, there is nothing to store the bit that is in the square brackets, there is no space to store this particular number, and this is lost, this is just tossed away by during addition, after the addition, and the result would be erroneously reported as 001, that is just 1 unsigned decimal 1. Now, that is something we can look at or relate to as the milometer odometer reading after a certain range 99999, and then it again goes back to 00000. It is something like this, not something, it is exactly like this, because there is no extra space to carry that to store that carryover bit, and that carryover bit is lost, and we start all new in the same cycle. So, the results are cycled back into the same range of numbers. So, this is the only error that can happen in a integer arithmetic, and one has to be careful about this overflow error. This can happen very silently, and no one would know, no error, no warning is issued, and we may be wondering what is going wrong if we are not aware of this particular type of error. So, as I said, the result of the computation is wrapped back into the range of admissible numbers, in this case 001, and this error is very silent. I mean, it is like a silent killer. Here we may compute happily and use the results happily without even knowing that this result is actually the wrong result. Now, coming back to the real numbers, the floating point numbers. So, scientific computations involve numbers of magnitudes ranging from very small to very large. Just for an example, gravitational constant is a very small number, about 6.6 multiplied by 10 raised to the power minus 11 Newton meter squared per kg squared, and compare that with Young's modulus of steel, that would be 2 into 10 raised to the power 11 Newton per meter square. Now, these are two, I chose these two numbers for the similar range of exponent of 10. So, one is 10 raised to the power minus 11, the other one is 10 raised to the power plus 11. Now, this is a wide range, and of course, there are mass of electrons, very small number, the speed of light, and energy during atomic reaction, atomic fission, or very large numbers. So, we have to deal with very small numbers and very large numbers, and obviously, no computer can accommodate, can have the storage to represent these numbers as integers. I mean, the word length that would be required would be humongous, and that would be simply beyond the capacity of even the largest computer to deal with such kind of numbers, provide this kind of range. So, we have to find a mechanism of doing computations which can deal with very small numbers as well as very large numbers, and that is what we use floating point numbers we call them. And the separator between the whole part, I mean this is the floating point number, as you can see this decimal point that can be shifted by suitable change in the exponent field. So, 6.6732 multiplied by 10 to the power minus 11 can be written as 0.66732 multiplied by 10 to the power minus 10. So, the decimal point, that is the separator between the whole part and the fractional part, that can be floated around by change in exponent, and that is why it is called a floating point representation. So, the standard format for a floating point number in any base, I mean it can be what we show, what we are seeing these numbers, I have written it in decimal number system base 10, but it can be in any base. So, let us say if it is a base B, then it is written as B 0 plus or minus, that can be positive or negative, plus or minus B 0 dot, that is the separator, then B 1, B 2, B 3 etcetera up to n, that is the number of precision, and then multiplied by B raised to the power e is the exponent, whatever is the exponent number. So, B is the base of the number system. So, that is how you have that 10 there in the decimal number system, 10 is the base of the number system. Now, the important thing to note here in this floating point representation is the whole part B 0, B naught has to be a number between 1 and B minus 1. So, in case of decimal number system, it has to be, standard representation would involve whole part to be a number between 1 and 9, right. So, 0.66732 multiplied by 10 to the power minus 10 is not a standard representation. Standard representation is 6.6732 multiplied by 10 raised to the power minus 11. So, that is a standard representation. So, this is the floating point representation in base B. Now, what happens in case of binary representation? Digital computers work with binary base 2 encoding for enhanced reliability, and of course, if it is enhanced, binary coding requires more space to store the information. So, cost of storage is of course coming down, I mean it really does not cost much to store now. So, we can actually have large storage, and reliability of computers is much more. So, if the base is 2, if the base of the number system is 2, then very peculiar thing happens here. The whole part B 0 has to be only 1 always, it can always be 1, B 0 has to be between 1 and 1. So, that is, there is no choice, the number is always 1 point something multiplied by 2 raised to the power something, and that is how we deal with it. And once it is done that it has to be 1, then we can just assume, considering that, I mean keep in mind that storage was not so cheap always. In 1970s, 1960s, it was very precious commodity. So, it did matter a lot if we could save even a single bit in one number representation. So, now when look at this from that perspective, if I can save 1 bit for by not storing something that is that I can assume to be there always, that is the whole part of this mantissa, B 0 is equal to 1 always, then I do not need to store it. I can only always assume that it is always there, 1 is always there. So, the number becomes 1 point something B 1, B 2, B 3 multiplied by 2 raised to the power something. Now, the implication of this is the number 0 does not exist, it is always something 1 point something something multiplied by 2 raised to the power something. So, 2 raised to the power may be something negative, some large exponent, but that still is a very small number, but still not equal to 0, and that is a very crucial thing that we need to understand, that absolute 0 does not exist on floating point numbers that are available on digital computers. In other words, I would like to emphasize, it is impossible to arrive at a result that is equal to 0 by way of computation on a digital computer. Think about the enormity of this statement, and we will continue from this point in our next lecture. Thank you.